Hi, I'm Gavin Cabral. This is the video for the final design project for computational multiphysics. For my main contributions, we're helping brainstorm build the 2D and 3D flex models, doing the 2D implementation of the report, and writing the scripting optimization portion of the report. For our problem, we designed a cantilever resonator made from piezoelectric with two metal layers that wrap around the piezo as seen in this diagram here. We use X-cut alpha quartz for our piezoelectric and golden tungsten as our metal layers. Our resonator will have a window on its length spanning the width that will be used as a deposit for thin films of chlorinated polyvinyl chloride, or CPCV. Our device will also be kept at a room temperature of 293 Kelvin, affected by an advanced cooling system on the exterior faces. The goal of our setup is to find the optimal mask position along this length that will allow our beam to have the greatest sensitivity in response to the added mass of this mask. Beyond our fixed geometry, the noteworthy variables for optimization are the total thickness of our beam in X, which will range between 200 micrometers to 800 micrometers, where one metal layer must be 4 times thicker than the other, and also the tip ratio of how far the metal wraps around the piezoelectric must be between 5 and 15% of the total beam length, and the position of this mask must start anywhere between 20% up the beam to 70% up the beam. So to outline the optimization steps, first we're going to want to find the optimal thickness ratio of the 3 layers without the mask that yield the greatest amount of curvature for a given field in the quartz, and this will also include the decision of making gold or tungsten the thicker layer. The second step is to find the optimal dimensions of the resonator without the mask to minimize the thermal effects so that they don't hinder the resonant behavior, because since the thermal effects will tend to only aid bending in one direction and dominate over the piezoelectric effects in steady state, if we take our first resonant mode here and we say that the thermal effects would have it bend in this shape, when the shape goes to bend the other way, the thermal effects will be thus hindering its ability to resonate because it will be pushing it back the same way it came. And then after this, we will use our optimized resonance structure to optimize the mask position as was initially desired. Some key things to understand before we build the model. For piezoelectricity, the direction and magnitude of strain in the piezoelectric effect in response to an applied voltage, which creates a field, will be calculated by this matrix right here. For volumetric heat generation, that will be calculated according to Joule's law, and then the heat flow will be governed by the heat equation. This is the time-dependent version. We'll be using the independent version for our steady-state solution, but nevertheless, Q dot here is volumetric heat generation, which describes the rate that heat is generated in the volume, and then the divergence of the rate of heat flow shows how much the rate of heat flow is flowing into a given volume element. Now, since this will be causing strain, to account for that, in our strain equation, we'll be using the coefficient of thermal expansion and the change in temperature to account for that. And in terms of resonance, we'll be using the dynamic beam equation, which describes the relationship between the acceleration in the y direction to the fourth derivative of displacement with respect to movement along its length. And our solution of this will involve a harmonic solution into the equation, and then separating it to solve for the time-independent portion with the cantilever boundary conditions for our specific problem. So to build our model, first we initialize our variables, our beam dimensions, and then we go on to optimize the ratio of thicknesses. So this is gold to piezoelectric, where tungsten will be 4 times the gold automatically. So accounting for all that, we use static physics to solve for the maximum curvature, which we find at this ratio right here. That ratio is then used to define the rest of our geometry in Flex. Then we define our material properties for thermal expansion piezoelectric effects. Here is the region for piezoelectric effects, noting that from our piezoelectric strain matrix, we can see that a field in the x direction will cause strain in the y direction. So we want to set our longitudinal direction in that y to allow the piezoelectric to cause the cantilever to curve. Then we define our gold region and our tungsten region, and this is the resulting simulation. The simulation is given power through implementing the necessary differential equations, including the time-dependent heat equation. Here are the strain definitions and Hooke's law of voltage relationships. Here's that independent heat equation that was used, and this is the deformation just from piezoelectric effects. Here's the deformation with both piezoelectric and thermal, where we can see e to the negative 5 is much greater than e to the negative 10, which means our thermal defects are indeed dominating over piezoelectric. Following such a greater tip displacement when the thermal effects are active, if we choose to optimize for minimal tip displacement, we theorize this will negate those thermal effects. So that's what we chose to optimize for. With that geometry, we then implemented the modal syntax and simulated the first 2 modes with their resonant frequencies. And if we go down and simulate the same thing in Maple, we see the same shape, thus validating the shape, and very similar frequencies, thus validating the frequencies. We can then add the mask region and recognize that increasing flexural rigidity of the beam will cause the frequency to rise, and adding mass will cause it to drop. So if we simulate our mask towards the edge, we're going to increase the flexural rigidity, but since the mass is overpowering, it's going to decrease the frequency, which we see here. And the same thing conversely will happen with an increase in frequency when we put it towards the base. In testing, we expect to see everything scale with respect to the boundary conditions on the exterior faces. So if we decrease the exterior faces' initial temperature, we can see the maximum it reaches is lower. If we increase it, we can see it gets higher. If we increase the voltage applied in the center, we can see the same thing happens. Conversely, when we lower the voltage, the same thing happens. For the voltage, we can see the contour decrease when we lower the voltage applied, and we don't see the contour increase when we increase the voltage applied, and we can see the gradient only along the dielectric as expected. And then in displacement, we see it displaced in the x as expected. From the piezoelectric effect, we see it curve to the right as expected. And again, it scales when we increase the voltage, tip displacement gets higher. From temperature, we see it increase to the right as expected because gold will be expanding more than tungsten alongside the linear increase. The optimization used for tip displacement can be seen in this flowchart here, starting from main, defining the initial conditions, then executes a zoom grid search. We graph the results, and then that ends. The grid search flowchart is a basic nested loop function for tip ratio and beam thickness, as is seen here. And the zoom function just iterates grid searches over smaller and smaller ranges, making sure that they never go over or under their respective bounds in the range. Here's the optimization output for minimum tip displacement. Here's the main optimization process for mask location for maximum sensitivity. Here's the grid search flowchart for the frequency optimization, which is the same as the tip displacement one, but with 1 less variable. And this is the zoom function for the frequency optimization, which is the same as tip displacement, but with 2 less bounds to check. Here's the output for the optimization for frequency. So in conclusion, here are our final optimized values on screen right here, and it's important to note that a time-dependent solution would have been better so that we could have accounted for the out-of-phase effects of the temperature and piezoelectric expansion and deformation, but this is the best we could do within the limitations of Flex.